Have you ever noticed how the sharpness of a lemony drink fades over time? That's because concentration matters, and in chemistry, it changes everything. Hello, learners. Today, let's explore a very practical idea: how electrode potentials are affected when conditions are not ideal. You see, standard electrode potentials assume that every solution is exactly 1 molar in concentration, but that rarely happens outside the lab. Imagine a metal ion like M to the power n plus reacting with n electrons to form solid metal M. In reality, if the concentration of the metal ion isn't 1 molar, the potential of the electrode changes. This is exactly why Nernst gave us a formula to bridge the gap between ideal and real conditions. This equation helps us determine the actual electrode potential when concentrations deviate from standard.
Let's get into the heart of it, the Nernst equation. Consider a half-cell reaction where a metal ion with charge N plus gains N electrons to become solid metal. The potential of this electrode at any given concentration is calculated using a formula that includes temperature, number of electrons transferred, and the concentration of the ion. The equation says the electrode potential equals the standard electrode potential minus open bracket the gas constant multiplied by temperature close bracket divided by open bracket the number of electrons multiplied by Faraday's constant close bracket, and this entire term is multiplied by the natural logarithm of the concentration of the metal ion. Now, when we take temperature as 298 Kelvin, the equation becomes simpler. It says the electrode potential equals the standard electrode potential minus 0.059 divided by the number of electrons multiplied by the logarithm base 10 of the concentration of the ion. And keep in mind, for pure solids like the metal itself, we assume the activity is 1. Let's bring this idea to life with a Daniell cell, a classic electrochemical setup involving copper and zinc. At the cathode, copper 2 plus ions gain 2 electrons to form solid copper. At the anode, solid zinc gives up 2 electrons and forms zinc 2 plus ions. To calculate the electrode potential at the copper electrode, we use the Nernst equation. It tells us the electrode potential equals the standard electrode potential minus 0.059 divided by 2, because 2 electrons are involved, multiplied by the logarithm of the copper 2 plus concentration. Likewise, for the zinc electrode, it's the same formula, but now we plug in the concentration of zinc 2 plus ions. The net cell potential is obtained by subtracting the anode potential from the cathode potential. This gives a new expression that includes both concentrations. The final form says the cell potential equals the standard cell potential minus 0.059 divided by 2 times the logarithm of the concentration of zinc 2 plus divided by the concentration of copper 2 plus. What does this mean? Increase copper ion concentration and the voltage goes up. Increase zinc ion concentration and it goes down.
Now let's generalize this concept. Imagine a redox reaction where smaller moles of substance A react with small b moles of substance B to produce small c moles of substance C and small b moles of substance D. We calculate something called the reaction quotient, denoted by capital Q. It is the product of the concentrations of C raised to the power C and D raised to the power D divided by the product of concentrations of A raised to the power small a and B raised to the power small b. The Nernst equation for this redox cell tells us the cell potential equals the standard cell potential minus the gas constant times temperature divided by the number of electrons multiplied by Faraday's constant, all multiplied by the natural logarithm of Q. At room temperature, this simplifies to the cell potential equals the standard cell potential minus 0.059 divided by n times the logarithm of Q. This equation helps us understand how cell potential shifts as the reaction progresses.
Let's apply this with a real example. Suppose we have magnesium solid reacting with silver ions in solution. The reaction is magnesium solid plus to silver ions gives magnesium to plus in solution and silver metal. Let's say the magnesium to plus concentration is 0.130 molar and silver ion concentration is 0.0001 molar. The number of electrons transferred is 2 and the standard cell potential is given as 3.17 volts. To calculate the actual cell potential, we use the Nernst formula. We subtract 0.059 divided by 2 multiplied by the logarithm of the ratio of magnesium ion concentration divided by silver ion concentration squared. That is, log of open bracket 0.130 divided by open bracket 0.0001 close bracket squared close bracket. After solving, we get a final answer. The cell potential is approximately 2.96 volts. This is a perfect example of how concentrations impact real electrochemical readings. Now, what happens when the cell stops producing current? At equilibrium, the forward and reverse reactions balance and the net cell potential becomes zero. From the Nernst equation, if the potential is zero, then the standard cell potential equals 0.059 divided by n times the logarithm of the equilibrium constant denoted by capital K. Let's say the standard cell potential is 1.1 volts and the number of electrons is 2. Multiply 1.1 by 2 and divide by 0.059, you get a value of about 37.3. That means the equilibrium constant is roughly 2 multiplied by 10 raised to the power 37, a huge number, indicating that the reaction goes almost completely to the right. So, we can actually calculate how far a reaction proceeds using just the electrode potential. Before we finish, let's connect this to thermodynamics. Did you know that the electrical work done by a cell is directly linked to the Gibbs free energy change of the reaction? Yes. The formula says Gibbs free energy change equals minus n multiplied by Faraday's constant multiplied by the cell potential. That means more voltage, more energy output. At standard conditions, this becomes standard Gibbs free energy equals minus an Fe naught cell. Take the Daniell cell as an example. 2 electrons, standard potential is 1.1 volts. Multiply and convert and you get negative 212.3 kilojoules per mole. That's a significant amount of energy and it explains why these reactions are so useful in batteries, in sensors, and even in biological redox processes. So, to wrap up, the Nernst equation is not just a formula. It's a bridge between concentration, energy, equilibrium, and real-life applications.